So this presentation is about standardization of variables. What does that mean? Well, it's a way of changing units of measurement. You can think of like changing a temperature from Fahrenheit into Celsius, or you can switch back and forth between pounds and kilograms. This is the same kind of idea. We're going to introduce a new kind of unit of measurement called a standardized unit. And the reasons for that will become clear in the course of this discussion. That's what we want to understand today. So here's kind of a silly story, not terribly realistic. There we go. Suppose you go to Mars. You're on a mission to study the temperatures of Martians. You arrive and you meet a Martian. His name's Joe. He speaks English. He's happy to talk to you. He looks like a Geico gecko. You ask him, "So Joe, can I take your temperature?" He says, "Okay." He has an Australian accent. Fine. So Joe's temperature, X1, turns out to be 88 degrees Fahrenheit. Now, I'm calling that X1 because Joe's the first Martian you've ever met. When you come to Martian number 2, his temperature will be X2. So, if that's all I tell you, then based on your knowledge of Martians, is Joe a hot or a cold Martian? So, of course, you don't know if Joe's a hot or a cold Martian because if you're like me, you don't know anything about the distribution of temperatures of Martians. So there's missing information. Well, what would you need to know to decide if Joe is hot or cold? You need to know the population mean of the distribution of temperatures of Martians. So you can decide if Joe's temperature is more or less than average. So you couldn't tell if Joe was hotter or cooler than average because you didn't know the population mean. But if I tell you that the population mean is 86 degrees Fahrenheit, now you know that Joe's a hot Martian because his temperature is greater than the population mean. How much hotter than average is he? Subtract 88 minus 86 degrees is 2 degrees Fahrenheit. So he's hotter than average. But as Martians go, is that just a little bit warm or is that really smoking hot? I mean, is 2 degrees a big deal for Martians? So once again, there's some missing information. Joe's 2 degrees hotter than average. Is that a big difference? Well, what is it that we need to know in order to find out? So what you need to know is the standard deviation of the distribution of temperatures of Martians. And if you know that, then you can decide if Joe's distance from average, that 2 degree difference, is really large or not. Now, if I tell you that the standard deviation for Martian temperatures is 0.5 degrees Fahrenheit, what you know then is what that means is that on average, Martians are about half a degree different from the average Martian. So Joe's 2 degrees away from average, but your average Martian's only half a degree away from average. So, how many times the average distance away from average is Joe? He's take the 2 degrees difference that Joe has, minus the ½ degree difference that your average Martian has. Divide, and Joe's 4 times as far away from average as your average Martian. So we say he has a temperature of 4 standardized units. His temperature is 88 degrees Fahrenheit, or you could say his temperature is 4 STDs. It's just 2 different units of measurement, like Celsius and Fahrenheit. STDs here is just another unit of measurement for the temperature. So Joe's a smoking hot Martian because he has 4 STDs. Okay, he has a z-score of 4 STD. That's big because it's 4 times as far from average as your average Martian would be. Just a few comments on notation here. So if I was talking about Joe's temperature in degrees Fahrenheit, the random variable for that would be this capital X. That's a function. You give it a Martian. It gives you the temperature of the Martian in Fahrenheit degrees. And then Z, it's the random variable for temperature in standardized units. You give Z a Martian as input, and it gives you out that Martian's temperature in STDs. Those are the capital letters, and then the corresponding lowercase letters are for the value of the variable. So capital X applied to Joe gives you back a temperature little x, which would be the 88 degrees that we observed. The lowercase z is a value for the variable capital Z. Then when you put the little subscripts on there, xi is the value of x for individual I. So since Joe is individual 1, you'd say x1 is 88 degrees Fahrenheit. Come to the next Martian, x2 would be whatever. The z's with the little subscripts, the lowercase, those are standardized values of variable z for individual I. So you can convert units back and forth between the natural units x and the standardized units z. If you know the x and you want to find the z, you use this formula, z equals x minus mu, and divide by sigma. On the other hand, if you want the z, you want to find x is mu plus z sigma. Those two formulas are, those two equations are equivalent, they're just rearranged, carry the same meaning as each other. And so you could go back and forth. And I have a few exercises in the workbook that students say they look be kind of silly exercises. Well, they'll have an x and I'll tell you to convert it to a z, and then in a minute I'll have you take the z and convert it back to an x again. And say, well, of course I'm going to get the same thing, so why should I do that? But in fact, very often people don't get the same thing. And that can happen in 2 ways. One is if you're not getting the order of operations right on your calculator. And then the other way it can happen is if you're rounding off intermediate steps. And so by converting and then converting back a couple of times in this series of exercises, that's how you find out whether you're doing it right. Okay. Anyway, so just to recap, what is this z all about? It's a measure of relative standing. It tells you where your x value stands relative to all the other x values in the population. That's it.